So welcome back everybody to our Gamma seminar. Today we have the pleasure to guest Anna Bălibanu from the Louisiana State University, who is going to talk about the reduction along strong Dirac maps and work with, I don't know, Maxence Mayrand, I'm sorry, your colleague. So thank you very much, Anna, for accepting our invitation. The floor is yours.
Yeah, thank you. So thank you for the invitation to speak in your seminar. Like you said, everything I will talk about today is joint work with my collaborator, Maxence Mayrand, who is your speaker for next week. So, so probably these two talks will have a similar flavor. So I want to talk about the kind of general reduction procedure that we developed along these maps that are called strong Dirac. And I'll say what these words mean, but first I want to begin with just a kind of motivation for a particular problem that kind of led us to this project and that we wanted to understand. So we'll start in the setting of what are called quasi-Poisson structures. So for these, I'll take G to be a semi-simple algebraic group over C. Instead of algebraic group, you can think a Lie group over C, and without kind of losing anything, you can imagine for the rest of this talk that this group is just SLN with coefficients in the complex numbers. And then I let factor G be the Lie algebra of this group. And because the group is semi-simple, the killing form, which is defined in the usual way, is non-degenerate on this Lie algebra. And this killing form gives us a canonical way to identify the Lie algebra G with its dual G star. So, so using this data, I can bring in some more players. So I can define something called the Cartan 3 form. This is an invariant element of the cube wedge of G, and it's defined in the following way. So it's a 3 form that takes 3 elements x, y, and z in the Lie algebra, and then applies the killing form to x and the bracket of y and z. And this is a 3 form which under the identification of G with G star becomes an element of the cube wedge of G, which is called the Cartan 3 tensor, and which I denote by this letter chi. So the observation is that if my group G is acting on in this case, a holomorphic manifold M, I get this infinitesimal action map that is a map that assigns to every element of the Lie algebra a vector field on M in a way that's compatible with the Lie brackets. And in particular, to this 3 tensor, which is an element of wedge cubed of the Lie algebra, it's going to assign a wedge of 3 vector fields, which means a tri-vector field on M that I'll denote by chi sub M. So the punchline is that from any action of the semi-simple algebraic group, we get a kind of canonical tri-vector field on the manifold. And then we can make the following definition, which is due to Alexeyev and Kozman-Schwarzbach and Meinrenken. So a quasi-Poisson structure on this manifold M that's being acted on by G is a bivector. So an element of a section of the squared wedge of the tangent bundle that's invariant with respect to the group action. And that has the property that when I take the Schouten bracket of pi with itself, I get this canonical trivector field that comes from the Cartan 3 tensor. So what you can think, normally if pi was a Poisson structure, then pi bracket pi, the condition for pi to be Poisson is for pi bracket pi to be equal to 0. And this guy is usually called the Jacobiator. So this is equivalent to the Jacobi identity. So in the case of quasi-Poisson structures, what's happening is that the Jacobi identity is being kind of twisted. So instead of the left-hand side of the Jacobi identity being equal to 0, it's equal to this tri-derivation chi sub M. So in particular, you can notice that if the group G was a trivial group, then this chi sub M is just 0, and then we recover the usual notion of Poisson structure. So we should yeah.
Sorry, Anna, one question, because as you started writing this canonical threefold, after this, I remember that there is a twisted Poisson structure defined in a canonical way on Lie groups, yeah, in under 13 associations. Maybe it's a kind of this quasi-Poisson structure too, yeah, because it's the background form, as it's called, is the canonical one. Is the formula you gave, maybe, I think, isn't it?
Yeah, so what do I want to say? So twisted Poisson structures, if I remember correctly, in the twisted case, I'm supposed to have something like this. So pi bracket pi is supposed to be pi sharp of some of some three-form twist.
Yeah.
Right.
And Lie groups, yeah. Sorry, go on.
I don't know if in the particular case of the group G, the quasi-Poisson structure that I will introduce is also a twisted Poisson structure. In general, they're different. So in general, chi-m is not in the image of pi sharp, but you're right that in some particular cases it
I tell you because it's not written straightforwardly in the literature. Okay, that's these both things you are talking to, but we wrote a paper lately. We tried to understand this structure on Lie groups. Yeah, this twisted Dirac structure defined on it, in particular the twisted Poisson structure related to it, and it came to it showed up that the free form we had, it was G invariant free form with the Poisson bracket, something of this sort. But I'm not sure. It's pretty much, it looks pretty much the same, but I'm not sure. That's why I was asking.
I'll give so on the next slide, I'll give an example that is a quasi-Poisson structure on the group G itself, and then we can look at that, and maybe that will look more familiar.
Yeah, sure. Thank you.
Yeah, so these quasi-Poisson things, we should think of them as kind of like deformations of Poisson structures, and the thing that is deforming is like a twist that comes from the group action. And then there's a whole kind of dictionary of things for these quasi-Poisson structures. So there's a notion of moment map. In this case, moment maps take values in the group G instead of the dual of the Lie algebra, and we say that something is a moment map if it satisfies a multiplicative analog of the usual moment map condition. And in that case, the quasi-Poisson manifold is called Hamiltonian.
Excuse me. Could you explain once again how do we define this chi-m, this three vector field, because it wasn't clear to me?
Yes, so I go back to the first slide. So first I define a three form on G. So this is an element of the wedge cubed of G star. And this is defined just by an explicit formula that uses the killing form. But then there's an isomorphism between the wedge cubed of G star and the wedge cubed of G that comes by identifying G and G star under the killing form. And that gives me an element chi in wedge cubed of G. So now when G is acting on a manifold, any element of the Lie algebra becomes a vector field on that manifold through this infinitesimal action map. And in particular, this element of wedge cubed of G becomes an element that is a global section of wedge cubed of the tangent bundle of M, which is the same thing as a trivector field. And this is how this chi-m is defined.
Okay, thank you very much.
Great. So we have these quasi-Poisson manifolds. There's a notion of moment map for such manifolds, and if they have a moment map, we call them Hamiltonian. And there's also a stratification that is a counterpart to the usual like symplectic foliation of a Poisson manifold, where M in this case is stratified by leaves, and each leaf carries a two form that's called a quasi-Hamiltonian two form. And this is potentially degenerate, and it's not closed. Instead, it has the property that its differential is minus the pullback of this Cartan three form that we defined on G through the map mu. So the two forms that appear in this quasi-Poisson setting also get like a twist, in the sense that instead of being closed, now their differential is twisted by this piece that comes from the group action. So I pause for more questions.
I think it's okay. Thank you.
So let's see a couple of examples. So my first example is the group G itself acting with an action of G by conjugation. And in this case, there's a canonical quasi-Poisson structure that's called the Cartan-Dirac structure. And I define it in the following ways. So I take an orthonormal basis of G with respect to the killing form. And then I make the following bivector for each element of this orthonormal basis. I take the left invariant vector field and the right invariant vector field, and I wedge them together. And I sum all of these, and then I normalize by an appropriate factor. And this gives me a bivector that's independent of the choice of orthonormal basis. This is an easy linear algebra check. And this bivector is quasi-Poisson in the sense that it satisfies this condition that pi bracket pi is equal to this Cartan 3 tensor. So the moment map in this case is just the identity, and the quasi-Hamiltonian leaves of the structure are exactly the conjugacy classes. So we should think of this as being kind of a multiplicative analog of the Lie algebra equipped with the usual constant-Kirillov Poisson structure, in which the symplectic leaves are the coadjoint orbits. So I pause also on this slide to see if this is in fact related to these twisted Poisson structures that Javier was mentioning.
Yeah, pretty much. I mean, there are lots of analogs, but I should take a look carefully that, for example, the leaves are also conjugacy classes in this case. We have many things done for this example. Indeed, Julia, who asked before, did several calculations about it. So it's pretty much the same. But we should take a look at it very carefully. Thank you. It's interesting, very interesting for us.
Okay, so let me give a second example. So the second example is called the internal fusion double. This is a space that I call DG that's defined to just be a product of two copies of the group. And it's being acted on by G cross G, but in kind of a funny way. So a pair GH acts on a point AB in the sense that on A, in the first coordinate, it acts by left and right multiplication, and on B, it just acts by conjugation by the second factor. So so I'll say where this action comes from. Let me say that this has a quasi-Hamiltonian structure, so a quasi-Poisson structure with a single leaf. And it's also Hamiltonian, so there's this group-valued moment map, and the group-valued moment map is defined in the following way. So I take a pair A, B, and in the first coordinate, I conjugate B by A, and in the second coordinate, I just project down to B. So what we should think this example is like a multiplicative counterpart to the cotangent bundle of the group equipped with a canonical symplectic structure. So you can imagine that if I have the cotangent bundle of G, I can use left trivialization to identify it with group cross the dual of the Lie algebra. And if I do this, then the cotangent lifts of left and right multiplication look more or less exactly like this formula, except wherever I have conjugation, I should replace with the adjoint action. And the moment map for this trivialization looks exactly like this formula, except with conjugation substituted for the adjoint action. So this is some kind of literal counterpart of T star G in this multiplicative setting. So now what I want to do is I want to introduce some objects from representation theory that that we were interested in when we started to work on this project. And for this, I'll need a little bit of machinery. So I'll fix in the group G a maximal torus. And this maximal torus is going to give me an associated Weil group, which is the normalizer of the torus, mod the torus. So you should think that in SLN, maximal torus is a subgroup that's conjugate to the subgroup of diagonal matrices. And the Weil group is just the group of permutation on n letters, and it acts on the diagonal matrices by just permuting the entries. So, so then to any element of the Weil group, I can assign a parabolic subgroup. So a parabolic subgroup in SLN looks like a block upper triangular subgroup. So this is a subgroup of matrices of this form, and these groups have a canonical decomposition called the Levy decomposition, which means that I take the block diagonal piece of the subgroup. This is called L. And then the rest, so this is, in this case, it will be a unipotent subgroup with entries just all the way up in this right-hand corner, which is called U. So, so to W, I assign such a parabolic subgroup that has the property that when I take the Levy decomposition, the Levy component is generated by the roots of G that are fixed by the permutation W.
Sorry, Anna, the Levy decomposition you are talking about is nothing but the Levy decomposition of the Lie algebras pushed to the Lie group, yeah?
Yes, exactly. So I have this group, and in this group has a unipotent radical, which is this U, which is a maximal unipotent subgroup.
Yeah.
And I can find a complement to that unipotent radical, which is L. And then the group is going to be a product of those, L normalizes U, so this is going to be an actual product of subgroups.
Yeah, indeed. Thank you.
Yeah, and then I introduce this data. So L has the property that the roots that appear in these blocks are fixed by the action of the Weil group. Z we can think of as the W fixed points in L. So this is going to contain kind of all of the roots that are in L, but it's also going to contain only a subset of the torus elements, which are the torus elements fixed by the permutation action of this Weil group element. And then I take UW to be a subgroup of these unipotent matrices that consist of, I should think of, these are going to be roots up here that are flipped by the action of W inverse, so that they go into this U bar I denoted it, which is the transpose of the subgroup. So I mean, this, if you're comfortable with the Lie theory, then this definition is useful. And if you prefer not to think about it too much, then in 5 minutes I will give some examples of what these of what these guys actually mean in practice, and some of these examples hopefully will be a bit familiar. So in any case, we have this kind of Lie theoretic data associated to this Weil group element, and then we can define a slice based on this data, which is just going to be a submanifold of G that is a product of something in this unipotent subgroup times something in this reductive subgroup Z, and then right translated by this Weil group element. So this is, for the moment, this is just a submanifold of G. And then these slices were studied by a lot of people. So originally, very classically, an example of such a slice was introduced by Steinberg, and then over time, Han Lustig and then Sebastianov introduced more examples, and more recently, I think only last year, Duan studied these things in arbitrary characteristic. But like all of this work, all of the slices that appear in this work have like two important common features. The first is the observation that when I act on the slice by conjugation by the unipotent subgroup U, I land in this larger space called omega. And the theorem says that this action map is actually an isomorphism. So I should think of sigma as being like a perfect cross-section to the action of U on omega. So in particular, the action of U on omega is free. And a consequence of this fact is that the slice sigma is transverse to all the conjugacy classes that it meets. And this is like the big punchline about these slices sigma, that they form transversal slices to the conjugation action in the group G. And there's one such slice for every element of the Weil group. So let me give an example. The distinguished element of the Weil group that I could consider is called the Coxeter element. So the Coxeter element is the product of all the simple reflections. In SLN, the simple reflections are reflections of the form I goes to I plus 1. So if I take the product of all such simple reflections, then I will get the cyclic permutation that cyclically permutes the n letters in order. And in this case, this element doesn't fix any points in the torus, right? Because if I cyclically permute the elements of the torus in SLN, I'm not going to have any fixed points. So this means that Z is just the identity, and the resulting slice that I get is this unipotent subgroup translated on the right by this permutation C. And this was the original slice introduced by Steinberg, and he proved some things about it. So he proved that all of the matrices that lie in the slice are regular, which means that their centralizer has minimal possible dimension. And that the slice intersects every conjugacy class that it meets exactly once. So this is like a strictly transverse slice to the conjugation action, in the sense that it intersects every orbit of the conjugation class's action in a single point and transversally. And there's a really concrete example of the slice that is maybe familiar from linear algebra. So in the case of, I wrote here SL4, but this is going to be the same story for SLN. In the case of SL4, this Coxeter element is the permutation corresponding to 1, 2, 3, 4. So if I write a matrix for this and I want it to live in SL4, it's going to look like this guy. So this is my permutation matrix C. And then if I translate this matrix on the right by the subgroup UC, I'm going to get this the space sigma C that I wrote down here. And you maybe recognize this as the space of companion matrices. So sometimes in linear algebra, we learn that every regular matrix in SLN or GLN is conjugate to a unique matrix of this form that has ones below the main diagonal and some entries in the top row and zeros everywhere else. And in fact, these entries are coefficients of the characteristic polynomial. So in the same way that companion matrices kind of parametrize the regular classes, the regular conjugacy classes in SLN, the Steinberg slice parametrizes the regular conjugacy classes in a more general semi-simple complex Lie group. And the theorem that we saw on the previous page says that or I guess that we see over here in the special case of the Steinberg slice, says exactly this, that every companion matrix is a regular matrix, and that every regular matrix is uniquely conjugate to a companion matrix, which in this case is determined very explicitly by the characteristic polynomial. So I welcome questions, especially about the representation theory part, which I know is probably the least familiar part of this talk for this audience.
For me, so far it's okay. Right? I had these things during my studies, but yes, a comment a little bit aside. In Spain, when I was studying, maybe I had the only place where this was taught during the degree. And maybe the United States is much better.
Yeah, so actually, I didn't know about companion matrices until after I learned about the Steinberg slice, and then I was giving a talk about it once, and someone told me that this is something that's sometimes taught in linear algebra, but I had. To me, this was totally new. So I think that's whether you've seen, especially this example, whether you've seen it before or not, it really depends on which country you learned linear algebra.
Yeah, I mean, I had a crazy course on linear algebra. I was studying in Spain, a very special place when we had many now famous people working in different things. And our algebra was crazy. So companion methods, it was like, many, let us say, very advanced results I had during my first year. But in worse is pretty much, we have a pretty much good level with students who have very advanced algebra, and even here it's you will not find it. Anyhow, I think that you can continue. If no one asks, don't worry. In any case, this is recorded, so times people then they can see it again. Thank you.
Okay. Yeah. So going back to this theorem, this theorem tells us that these slices sigma define transversal slices to the conjugation action, and then a kind of motivating question that we wanted to answer is the following. So this group G has a quasi-Poisson structure, which is this Cartan-Dirac structure that we defined a few slides ago. And the leaves of the structure are the conjugacy classes. And inside of G, I have these spaces, sigma and omega, that are transverse to the conjugacy classes. So they're also, in some sense, transverse to this Cartan-Dirac structure. And we wanted to understand, what sort of structure is induced on sigma and omega by the quasi-Poisson structure on the ambient space. And I guess two observations that I want to make about this question is that first of all, remember sigma is defined as U, W, Z, W. And then I also have the space omega that is a product of U, Z, W, and U. So both of these have actions of Z by conjugation because the subgroup Z normalizes U, W, and it normalizes the U's, and it commutes with W. So this action is well defined. And then also from both of these spaces, I can project onto the Z components. So I also have these equivariant projections from sigma and omega to Z. So using these observations, I'm going to tell you the answer to this question, and then I will tell you how we prove the answer. The first theorem is the following, that if I have a quasi-Poisson moment map, so this is a moment map valued in the group G with the Cartan-Dirac structure, then I get the following diagram. So I can take the pre-image of these two spaces, sigma and omega, through this moment map. And omega has an action of U that I can quotient by. And remember that this omega is like the free U saturation of sigma. So when I make this quotient of omega by U, I get something isomorphic to sigma, which means that also if I take these these pre-images, I'm going to get an isomorphism between the pre-image of sigma and the pre-image of omega quotiented by u. So this quotient in particular always exists. And then I have a kind of another piece of data, which is these maps to Z that just come from composing, here sigma and omega live here, and they both have natural projections onto the Z components. So if I compose these natural projections with the moment map, I'm going to get these blue maps over here going to Z. And also on these spaces, I have actions of this reductive subgroup Z. And the statement of the theorem is that the Poisson structure, the quasi-Poisson structure on M, induces quasi-Poisson structures on these two reduced spaces, but now the structures are quasi-Poisson for the action of the subgroup Z. So this is some kind of reduction where we've gone from a quasi-Poisson structure for G to a quasi-Poisson structure for a subgroup. And in particular, in the Coxeter case that we were talking about earlier that corresponded to the case of companion matrices in SLN, this group Z is a trivial group. And so being quasi-Poisson for the action of a trivial group is the same thing as being Poisson. So in this Coxeter case, we get Poisson structures on these reduced spaces instead. So let's do an example where we see this theorem in action. So we had this example of a quasi-Poisson manifold, which was this internal fusion double DG, and in the target of the moment map for DG, I have a product of two copies of the Coxeter, this Steinberg slice, which is like the space of companion matrices. So I can try to take the pre-image of the subspace under mu, and then I'm supposed to get according to this corollary, I'm supposed to get a Poisson structure on the resulting space. So if I try to take this pre-image, the first observation is that the image of mu is just the space of conjugate pairs inside G cross G, just looking at the definition of this map mu. So this means that if I take the pre-image of the Steinberg slice, we said that the Steinberg slice intersects every conjugacy class in exactly one point. So this means that if two elements of the Steinberg slice are conjugate, then they must be equal. And that means that if I take the pre-image of a product of two copies of the Steinberg slice, this is the same as the pre-image of the diagonal copy of the Steinberg slice. And it's very easy to see what the pre-image of a diagonal point is under this map mu. So what I end up getting is the space of pairs A and B in the group across the slice with the property that A centralizes B. And this is I denote by this fractor Z. We should think of this as kind of like a family of centralizers of elements that are parametrized by the Steinberg slice. So like in SLN, this would mean that I take the space where like the base is the space of companion matrices, and in every fiber, I put the centralizer of that particular companion matrix. So this is a pretty well-known group scheme in representation theory, which is called the universal centralizer. And what we just proved about it is that it's a symplectic manifold. So it's the previous corollary tells us that that the space gets a Poisson structure through this reduction, but because DG is a quasi-Hamiltonian space, so it's like a non-degenerate quasi-Poisson space, the resulting Poisson structure on Z is also going to be non-degenerate, which means that it's going to be symplectic. So this is a fact that's known classically and was known for a long time before even quasi-Poisson things were introduced, but this is just a way to recover this particular well-known structure using our theorem. So what I would like to do now is say a little bit about how this theorem is proved, and in particular how it follows from the kind of main theorem of our paper, which is this result about reduction of Dirac structures. So for this, first I'll give a kind of short reminder about Dirac geometry. So a Dirac manifold is a triple with three pieces of data. So M is a manifold, real or complex, it doesn't really matter, it will be the same definition. And L is a subbundle of the direct sum of the tangent bundle of M and the cotangent bundle of M. So this is a vector bundle over M that lives inside this thing, which is sometimes called the generalized tangent bundle. And eta is a closed three form on M. And these guys satisfy the following two conditions. So this bundle L is Lagrangian with respect to the natural non-degenerate pairing on this generalized cotangent bundle. And it's also closed with respect to this bracket, which is called the Courant bracket, that takes two elements of the generalized tangent bundle, and in the first coordinate, it outputs the Lie bracket of vector fields, and in the second coordinate, it outputs this slightly more complicated formula that is twisted by the appearance of this three form. So sometimes these are called twisted Dirac manifolds because of this eta, and then when eta is 0, they're called just regular Dirac manifolds. But for me, everything is always twisted, and so I just call them Dirac.
Here's one remark. Normally, the way you write the Cora bracket sometimes is called Dorfman bracket because it's two different kinds. And lately, some people are trying to focus on the findings of Dorfman. So they used to make some remarks on it all the time.
Yeah, so this definition fits into a much larger picture of Courant algebroids that I won't say anything about. But yeah, so the last thing I want to say about this is that when I restrict this bracket to a Lagrangian subbundle, then this little bracket becomes a Lie bracket.
Yes, one thing. Maybe there is one differential missing. Yeah. In the second part is the Lie bracket would be of beta minus differential contraction. Yeah.
Yeah, you're right. I made a typo. So this should be d alpha.
Yeah. Okay. Yeah, that's the point. Thank you.
Thank you. Yeah. So this bracket, when I restrict it to a Lagrangian subbundle, it becomes skew symmetric, and it satisfies the Jacobi identity, which means that it's a Lie bracket on the sections of L. And then L becomes a Lie algebroid over M, where the anchor map is just projection onto this first component that takes us to the tangent bundle of M. So this is Dirac manifolds. We should think of as a common framework in which to work with symplectic things, Poisson things, twisted Poisson things, quasi-Poisson things, and so on. So I'll give a couple of examples that are just the ones that are sort of relevant to what we do today. So if I have a symplectic manifold, I let eta be equal to 0, and then I can define a Lagrangian subbundle of this generalized cotangent bundle just by taking the graph of the symplectic form. So this means I take pairs of the form V and omega contracted with V, and this is going to be a Dirac structure on M that completely encodes the information of the symplectic structure. So if I know L omega, then I can recover omega from it. And similarly, if I have a Poisson manifold, I let eta be 0 again. So I again get like a 0 twisted Dirac structure by taking the graph of the anchor map pi sharp. So this means I take all points of the form pi contracted with alpha comma alpha. And this is also a Lagrangian subbundle of the generalized cotangent bundle that's closed under this bracket. And this follows from like skew symmetry of the Poisson structure and from the Jacobi identity of the Poisson structure, and it encodes all the information about the bivector pi. So if I know L pi, I can recover pi. And then quasi-Poisson structures also fall inside this Dirac framework, but in this case, the twist is non-zero. So I start with a quasi-Poisson moment map. This I should have put here pi CD. This is what I called the quasi-Poisson structure on G. So if this is a quasi-Poisson moment map, then I let eta be minus the pullback of eta G, which is a 3 form on G. I pull it back to M, and I get a 3 form on M. And the bivector pi is going to induce a Dirac structure on M that's defined in a more complicated way. So in this case, the Dirac structure is not a graph generally. In the first component, it's given by elements of the form pi contracted with a 1 form plus an action vector field of the Lie algebra. And then in the second component, it's some function of xi and alpha that I decided not to try to write down because it's a bit complicated. But in any case, what we should take away from this is that quasi-Poisson manifolds can also be expressed in this language of Dirac structures, where they're going to be Dirac structures that are twisted by this 3 form minus the pullback of the Cartan 3 form on G.
Sorry, Anna, one curiosity, because in the case of general Dirac manifold, well, without twist, normally said that it amounts to the fact that it's a stratification by pre-symplectic manifold. When you add the twist, you have some analog, yeah? And with the symplectic, Poisson, and multiplicative, when you reduce the structure to these leaves of the characteristic distribution, you obtain other structure. So my question is, when you have a quasi-Poisson manifold and you have the characteristic distribution associated to this structure, to this Dirac manifold, what do you obtain? Do you obtain something more? What type of structure you obtain in the leaves of the characteristic distribution when you restrict this thing?
Do you mean what do you mean by the characteristic distribution?
Okay. Yeah. Well, you have this Dirac subbundle, yeah, and you project into the tangent space to the manifold, yeah. You obtain a distribution that is integrable. Yeah?
Yes. So this is the spoliation of the Hamiltonian leaves.
Yeah. Okay. So okay. So the structure you obtain on it is what you said before. Yeah.
Yes. So the pre-symplectic structure that you get on every leaf is one of these quasi-Hamiltonian structures. So the leaves look like omega O, and this omega O it has a kernel in general. And it has the property, well, I guess this is the property of all pre-symplectic leaves, that when I differentiate omega O, it's not closed, but I get this minus pullback. So this is these are these like Hamiltonian structures. Yeah. So
great.
So all the things that I said about group valued moment maps, about quasi-Hamiltonian leaves, they all fit into the Dirac framework.
Okay, great. This is what I wanted to see. Thank you very much.
I should say that this is actually, I wrote it down as an example, but this is more like a theorem, and it's a theorem of Borstein and Kreinig. So quasi-Poisson structures were first introduced in the way that I introduced them, in this like very classical way, and then Borstein and Kreinig, they related them to the Dirac framework in a couple of papers. Okay, so there are these Dirac structures, and then I want to make an important definition that also appears in the title of the talk. So if I have two Dirac manifolds, M and X, and they have so each one has a Lagrangian subbundle that is the Dirac structure and also a 3-form twist. Then there's a special class of maps that I want to study. So a map from M to X is going to be called a strong Dirac map if it satisfies the following 3 properties. So the first property says that the Dirac structure on X is obtained from the Dirac structure on M by taking sort of all points of the form push forward of V comma alpha with the property that V comma, the pullback of alpha is an element of LM. So this is, if you're a bit familiar with Dirac structures, you know that this is the same as saying that mu is a forward Dirac map. So for example, all Poisson maps and all quasi-Poisson maps have this property of being forward Dirac. This is some kind of generalization of the push forward of a bivector. And the way that we should think of, what we should think that this property is saying is it's telling us that that the Dirac structure on Lx is a result of the Dirac structure on M. And then so far I've said that mu is forward Dirac, and then I wanted to satisfy two more properties that are not always satisfied by forward Dirac maps. One is that it's compatible with these two three-form twists. So the pullback of eta x is equal to eta m. And the next is that it satisfies this non-degeneracy condition that the kernel of mu star, or of the push forward of mu, I guess, intersects the Dirac bundle LM trivially. And so these are properties that are satisfied by all Poisson maps, but once we leave the Poisson world and get into the Dirac world or even the quasi-Poisson world, these two properties are not always satisfied by forward Dirac maps. And then the kind of the punchline of this definition is that it tells me the following thing. It tells me that whenever I take an element of the Dirac bundle Lx, there's a unique vector field on M that element came from under this forward Dirac map. So this means that for every element in Lx, I associate a W in Tm with the property that that W has kind of induced that element through Dirac push forward, and W is a pre-image of V under the differential of mu. So in particular, this gives me a well-defined action of the Lie algebroid Lx on the manifold M by just taking a pair V alpha and assigning to it this unique vector W. So this observation is kind of a mouthful, but it's actually it's a generalization of some facts that are probably familiar. So for example, if I have a strong Dirac map from some Dirac manifold M to the dual of a Lie algebra with the constant Kirillov Poisson structure, then it's not that hard to check that eta is 0, because eta is supposed to be the pullback through mu of the twist on G star, and because G star is Poisson, the twist is 0. Then it's not that hard to check that actually the existence of such a map implies that M is itself a Poisson manifold. So L is just the graph of a Poisson bivector, and then mu is a Poisson map. And we already know that whenever I have a Poisson map from a Poisson manifold to the dual of a Lie algebra, this induces on that Poisson manifold the structure of a Hamiltonian space. So it means that it induces on that Poisson manifold an action or an infinitesimal action of that Lie algebra that then may or may not integrate to an action of the group. So in the same way that that Poisson maps to G star are kind of in bijective correspondence with Hamiltonian G spaces, strong Dirac maps to a Dirac manifold X are in bijective correspondence with manifolds on which the algebroid of X acts by a Lie algebroid action. This is this is somehow the special case of this observation. And then in the quasi-Poisson case, we have kind of a similar story. So if I have a strong Dirac map from some Dirac manifold to G equipped with the Cartan-Dirac structure, then this three form on M is the pullback of the three form on G, which is minus the pullback of eta G. Then one can check that this manifold M is actually a quasi-Poisson manifold. So L is the Dirac structure associated to a quasi-Poisson structure. And this guy mu is a quasi-Poisson map, and in fact, it's a quasi-Poisson moment map. So so M gets the structure of a Hamiltonian quasi-Poisson manifold for the infinitesimal action of the Lie algebra G. So these strong Dirac maps, we should think of them as something that simultaneously generalizes moment maps in Poisson geometry and also moment maps in quasi-Poisson geometry, because they're maps that induce an action of the Lie algebroid of the target onto the source. So then in our paper, we make the following definition. So we say that a reduction level of this Dirac manifold X is a pair of two things, a submanifold of X and a two-form on the submanifold that satisfies the following properties. So the first property is that the differential of this two-form cancels out the pullback of eta x to the submanifold S. So we should think that the differential of gamma kind of untwists the twist on the Dirac structure of X when restricted to the submanifold. And the second condition is that the intersection of this Lie algebroid Lx with the push forward of the graph of gamma is, a priori, this is just a generalized distribution in the generalized cotangent bundle of X. And the condition is that this distribution has constant rank. And if this has constant rank, then it's actually a Lie algebroid, and we call it the stabilizer subalgebroid of the reduction level S gamma. So this is a new definition that kind of singles out a particular class of submanifolds of the target of a strong Dirac map. And then once we have this definition, we can formulate the following theorem. So if I have a strong Dirac map, like I said, I get a Lie algebroid action of the Dirac structure downstairs on the manifold upstairs. And if I take a reduction level of the manifold of the target, so of the manifold downstairs, that has some nice regularity properties. So it intersects this the strong Dirac map cleanly, so that the pullback or the pre-image of S is a submanifold of M. And the quotient of the submanifold by the action of the stabilizer subalgebroid exists. So is a manifold and with like a surjective submersion from the pre-image of S, which I call Q. Then we prove the following thing. We prove that if I take the Dirac structure on M, and then I take what's called a Dirac pullback to the submanifold, so I restrict the Dirac structure on the ambient space to the submanifold. This is something called a gauge transform. So I twist away the three-form twist of the Dirac structure, and then I push forward in the Dirac sense to the manifold Q. I will get a new Dirac structure on Q, and we show that this Dirac structure is actually Poisson. So we should think of this as like a reduction procedure that begins with a Dirac manifold and a strong Dirac map to a target. And then for particular submanifolds of that target, it does a reduction process where it takes the pre-image of the submanifold and it quotients by some symmetries, and it obtains on the resulting quotient a Poisson structure that's induced by the original Dirac structure.
Sorry, Anna, one question. How generalized are these reduction levels? I mean, which example do you have of that? You can retrieve some standard situation or something.
So I will, in the next slide, I will give a handful of examples.
Okay, thank you.
So the first example is where S is a point. So a reduction level is a point, and then the two-form is 0. And then the stabilizer subalgebroid is just the isotropy Lie algebra of the algebroid Lx at this point. So this is what's called Dirac reduction at a point, and it's just the Dirac version of like Marsden-Weinstein reduction at a fixed point in the target of the at a fixed point in the dual level Lie algebra, for example. So this is somehow this is the simplest example of a reduction level, that all points are reduction levels, and as long as they are regular or values of the moment map, then we can do reduction, or I guess of the strong Dirac map, then we can do reduction there. A larger class of reduction levels are the actual presymplectic leaves of the Dirac structure. So in this case, a reduction level is the presymplectic leaf O, and the two-form gamma is the presymplectic form on the leaf. And then in this case, the stabilizer subalgebroid is the restriction of the bundle Lx to this presymplectic leaf. So in particular, if X is the dual level Lie algebra with the KKS Poisson structure, then our theorem recovers just Marsden-Weinstein reduction along a coadjoint orbit. And if X is the group G along with the Cartan-Dirac structure, then this theorem recovers quasi-Hamiltonian reduction along a conjugacy class, which was defined in the same work of Alexeyev and Kozman-Schwarzbach and Mayrand. So these are kind of these reduction levels. They recover a lot of familiar examples of submanifolds along which we do reduction. And the kind of last example I want to give is the kind of general observation that when the two-form gamma is equal to 0, then the stabilizer subalgebroid is the intersection of the Dirac structure with the bundle that is the tangent bundle of S plus the annihilator of the tangent bundle of S. So in particular, in the case of a Poisson manifold X, the reduction level in this case is exactly what's called a pre-Poisson submanifold. And these were introduced by Cattaneo and Zambon. And then reduction in this setting was also studied in a paper of my collaborator Maxence together with Peter Crooks.
Sorry, can you tell me which one by Cattaneo and Zambon exactly? Which paper?
I think it's literally called Poisson submanifolds.
Oh, okay.
But I can send it to you. I don't remember the literal title.
No, I think that I will manage to find it. Thank you.
Okay, so these are examples of reduction levels that kind of already that were already studied before us, and then I want to give a particular example that came up before. So in our case where G is a semi-simple complex group, I take its Weil group and I take this Coxeter element that's just a cyclic permutation that cyclically permutes the n letters. And then the corresponding Steinberg slice is an example of a reduction level where the stabilizer subalgebroid is trivial. And its U saturation, which we called omega, is a reduction level where the stabilizer subalgebroid is the action algebroid of this unipotent subgroup U that we previously used to act with. And then our theorem about reduction levels recovers this corollary that I stated earlier in the talk, that if I have a quasi-Poisson moment map, I can reduce at the Steinberg slice or at its U saturation, and I get a Poisson structure on these reductions. So at least the special case of this slices where C is the Coxeter element, this case fits into this this reduction level perspective.
Okay, sorry, Anna. I just noticed that we surpassed the time we are supposed to finish. But anyhow, if you want to continue a little bit, you can. 5 to minutes, okay.
Yeah. So I also noticed that we're getting to an hour. So So in your email, you were kind of ambiguous about the length of this talk, and then you told me that it always takes longer than
yeah, it's not a problem, but you know, I started thinking about what you are doing. I absolutely forgot about it. I'm sorry. Just to tell you.
I do have a little bit longer to go, but I probably no more than 10 minutes.
Okay, it's fine. Please continue. It's not a problem.
Hopefully it will be okay. So the observation at this point is that we recovered this corollary, which I stated earlier in the talk, that in the case of the Coxeter element, we had these slices that were kind of related to the space of companion matrices, and reduction along these slices gave Poisson structures. But I also stated a more general theorem, which said that in the case where C is instead W, an arbitrary element of the Weyl group, these reduced spaces should be quasi-Poisson for the action of a subgroup. And so far we haven't recovered that result. So this is what I want to say in these final few minutes of the talk. And for this, I'll need a generalization of the previous definition that I gave. So we defined something called generalized reduction levels, which are like reduction levels with some extra data. So then the new data I put in blue. So a generalized reduction level is now it's not a pair anymore. So this is what happens when you copy paste. This is a triple. And it's a triple of three things. So a submanifold of X, a two form on that submanifold, and a smooth map of constant rank from the submanifold to some new Dirac manifold, which I call Z. And these three items are supposed to satisfy some compatibility conditions. So the compatibility conditions are first that the differential of this two-form gamma, previously it untwisted eta x, so this meant that the sum was equal to 0, but now the sum is a potentially non-zero value that comes from the pullback of this three-form on Z. Then there's a compatibility condition between the Dirac structure on X restricted to S and the Dirac structure on Z. And then this algebroid also gets kind of enhanced. So I take the intersection of the Dirac structure on X with the push forward of the graph of gamma, but then also with this kind of third subbundle of the generalized cotangent bundle. And I want this guy to have constant rank. And if this is true, then like before, it's a Lie algebroid, and we call it the stabilizer subalgebroid. And then we have a very analogous. Yeah, there's a question.
Yeah, sure. What more or less they come all these conditions? Because I know that there are natural generalizations of what we thought, but I get a little bit lost. Which is the idea of this all these conditions?
So previously, the conditions are like this. So you should think that that this first condition, what this first condition says is that adding, the picture that we should think of is S has a map into X, and then it has a map to Z. So this is I, and this is phi. And this first condition says if I take the three form on Z and I pull back to S, I don't quite get the pullback of the three form on X, but the difference is controlled by this gamma. So what we're going to see is that in the reduction process, this gamma plays a role because it corresponds to a gauge transformation of the Dirac structure. So this is condition one, and condition one is a compatibility condition between the three form on X, which is this eta X, the three form on Z, which is this eta Z, and this compatibility is controlled by the two form on the reduction level. The second condition, I put a lot of symbols, but it's not totally important what the symbols mean. What you should read them as meaning is I have this Dirac structure Lx on X. I can restrict it in the Dirac sense to S. Then I do this tau gamma is called a gauge transformation. So this is like an untwisting by gamma. and then I can push forward in the forward Dirac sense, and I will get a distribution on Z. And the second condition says that this distribution on Z is exactly the Dirac structure on Z. So this is like a compatibility condition between the pullback of the Dirac structure on X to S and the Dirac structure on Z. And this,
now I understand. Yeah, thank you.
So there are a lot of symbols, but somehow they're not as technical as they look somehow. And then this AS is supposed to be measuring kind of the kernel or like the degeneracy of the algebroid on X when I restrict it to S. So this is what's going to happen in the theorem, that this AS is the thing that's acting that I'm going to quotient by. And somehow in reduction, when I take a quotient, what I'm trying to do is like mod out the degeneracies of a restricted structure. And then we get a theorem just like before. So I take a strong Dirac map from M to X. And I take a generalized reduction level of X that has the property that it has these two regularity properties. So that the S intersects mu cleanly means that when I take the pre-image under mu, I'm going to get a submanifold of M. And then the quotient of this pre-image by the action of this algebroid is a manifold. So I get something smooth where this Q is. And then in this picture, I have some extra data. So S had a map to Z. And if I compose that map with the strong Dirac mu, I'm going to get a map from the pre-image of S to Z that looks like that's going to descend. So it's going to fit into this diagram. That's going to descend to a map on the quotient. And the statement of the theorem is that when I take the Dirac structure on M, so this is this LM, then I pull it back to the submanifold that is the pre-image of S. Then I twist or untwist, I guess, using a gauge transformation. And then I push forward along this map to Q. I'm going to get a Dirac structure on Q. So this is just like a formal pulling and pushing of Dirac bundles. And the statement of the theorem is that not only will this be a Dirac structure, but this descended map to Z is going to be a strong Dirac map, which is going to mean that so strong Dirac means that I get an action of the Lie algebroid on Z on this manifold Q. So again, this theorem has like a lot of words in it. So I want to illustrate it in this concrete example of the transverse slices that I started the talk with. So we said that in the quasi-Poisson case, to every Weil group element, we can associate a slice sigma and then its saturation omega. So sigma was of the form UW times Z times W. And when I conjugate sigma by this unipotent subgroup U, I get this larger space that I called omega. And these are two spaces that have Z actions. And they both have this kind of natural projections to Z, which are just picking out the Z factor in these products. And these will be concrete examples of generalized reduction levels in the group with respect to the Cartan-Dirac structure. So if I take sigma, and I take the 2 form to be 0, and I take this map phi to be the projection to Z, then this is a generalized reduction level whose stabilizer subalgebroid is 0. And if I take omega, and there's a particular choice of 2 form, and I take phi to be the projection map to Z, then I get a generalized reduction level whose stabilizer subalgebroid is given by the action of the Lie algebra of this unipotent group. And then our theorem tells us that if I have a quasi-Poisson moment map, then a quasi-Poisson moment map is an example of a strong Dirac map. And then these spaces fit into this diagram. So I take the preimage of sigma under this quasi-Poisson moment map. I take the preimage of omega. I can quotient the preimage of omega by u. And this where did I put it? Here. This isomorphism gives me this diagonal isomorphism between the preimage of sigma and the reduced space of omega. And both of these guys have residual maps to the reductive group Z. And our theorem tells me that that actually both of these spaces have Dirac structures and that these blue maps are strong Dirac maps. But a strong Dirac map to the group Z is the same thing as a quasi-Poisson moment map for the action of Z. So in this way, we get a quasi-Poisson structure on the spaces with respect to this residual action of the subgroup Z. So in this way, we recovered the kind of very first theorem that I stated that describes what happens when I take the quasi-Poisson structure on M and I restrict to preimages of these transversal slices in Z. And I think now I'm done.
Thank you very much, Anna, for your talk. So is there any question, remark, comment? No. Oh, okay, yes, I have a question, but it's a little bit away of the topic. I mean, have you tried to use this for certain physical systems or physical biased or motivated things? Because, you know, I have seen lately many new types of reductions with many types of structures by Catania, Rambon, and all these people. And sometimes, for example, when you have twisted Poisson and all the structures, they can be used to describe important systems, and these reductions are useful. And sometimes there are even papers talking about if some system can be described by means of twisted Poisson, almost Poisson, quasi-Poisson. So have you tried to apply this, or someone has tried to apply this type of reduction to some physical motivated example, some physical systems? Do you know something?
I think the answer is no. So I mean, because neither Maxence nor me are really like mathematical physicists or have a background in physics. The examples that we that we initially tested this construction on were closer to the things that we're familiar with. So we have you know, in addition to these slices, like various examples that come from representation theory or from Lie theory. We have some things that come from like mathematical physics in the sense of like TQFTs or something. But in terms of mechanical systems, I think we just are not familiar enough with them to have tried them. But if you have a particular example in mind, I would be really curious to understand how our construction relates to a lot of these other reduction type theorems that
I mean, I must confess that I had to take a look very carefully to what you did. I have with Yulia, for example, one of my PhD students that works about Dirac reductions in the twisted Poisson category with current algebras and things of the sort. So sometimes here my research crosses a certain line. What you did can be interesting, yeah. So we do these things from a mathematical point of view. Many of our papers are rather mathematical, yeah. But in many cases, we try to apply these things to physical problems. And sometimes, for example, when you talk about quasi-Poisson structure, for us is what we can describe by means of that, yeah, by means of these structures. That's why I'm asking. But on the other hand, I have to confess that thank you for your topic, because it's I have learned many things I never seen before, so I have to take a look. I just took a look at your nice paper. I wanted to learn a little bit about it. So for me, it's been a pleasure. Thank you, Anna. Is there any other question, comment, remark? No, so maybe we have to finish because we have a Zoom meeting too. So Anna, thank you very much. I hope that it was a nice talk for you too. We will send you the record.
Nice to meet
The
you.
recording.
Yeah, thank you all for attending. And just let me recall that next week we have Maxence Mayrand from the University of Sherbrooke, who I guess will continue talking about these things. We will send the title and abstract to everyone, so you will receive an email with information.
Well, thank you, Anna. Really, we
Thank you.
appreciate.
Bye-bye.
Bye. Thank you all.